So this next area I want to get into is on rotation right here. Now, you've probably been spinning your head from the beginning of the semester, so you're probably pretty good at rotation by now. But we're going to go back to everything we've learned before. We've only learned 4 things so far. We've only learned constant acceleration, forces, energy, and momentum. 4 things. We're not going to learn anything else for the rest of the semester. We're just going to apply it for different areas. But those are the 4 things. And we're not going to, and in chapter 9, we just apply it to 2 of the concepts, and then 10 will apply the other 2. So in chapter 9, we're only worried about constant acceleration. How does the constant acceleration equations, what are they for rotation? And the other one is energy. Chapter 10, they'll come back and do it for momentum and forces right here. But we're just going to look at these 2 right here. So now, first of all, when we look at something rotating, first of all, they're going to be solids. We're not going to be stirring around a liquid or a gas right here, which means if I draw 2 dots, like that dot and that dot, as this thing turns, that distance is always going to stay the same between 2 dots right there. Now, suppose I look at, let's say I have 3 dots here, and suppose this thing were to turn right here. Actually, I'm making 5 dots right there. If this thing were to turn right here, all these dots don't even go the same distance right here. This dot doesn't even move right here. You notice a little while later, this dot might be over here, this dot would be here, and so on. So they all move different amounts right here. So we don't want to, if we're going to specify a rotational distance, we don't want to use this distance here, because then it depends on where you're talking about. What we'd rather use is theta. They all went through the same angle. So what we'd like to use is this angle, theta, right there. And because they all turn through the same angle. And what's the relationship between the theta and the s? If we just, let me call this, say this distance right here is s. Well, s is just equal to the radius, which in this case, if it was just out to there, it'd be r times theta. So anytime you have a wedge, we could say, or theta is defined as the arc length divided by the radius. We can say theta is the arc length divided by the radius, or s equals r theta. S equals r theta. And you can see here at the middle, r is 0, so theta, and theta, doesn't have any meaning there, but that's non-zero, but that is 0. It's not going anywhere. The way out on the edge is where you get the most distance. So they're not going to agree on s, and they're not going to agree on r for different points, but they will agree on theta right here. So we like to use theta instead. Now, if this thing moved from here to here in the same amount of time right here, then you notice the speeds will be different right here. All the velocities will be different, but if we define the speed, angular speed, as the theta per unit time, then it would all be the same. So if we just took the derivative of this, what do we got? ds dt equals r is a constant for one little particle going around. R is a constant, so it's r d theta dt. Well, this is the definition of velocity, and this is our definition of angular speed, and we're going to give it a letter. We're going to call it omega. So this is angular speed. It has units of radians per second. Anytime you see theta by itself, don't even think of using degrees. Use radians right here. This is the definition of the radian. It's the arc length over the radius right here. So this tells me the speed right here. And you can see the bigger the r is, the faster they're going. Way out on the edge, you're going the fastest right there. All these points have the same omega, but the bigger the r, the bigger the speed. Now, if we wanted to take the next derivative, this would be dv dt equals r d omega dt. Well, this was our definition of acceleration. we're going to call this d omega dt angular acceleration. So this is r times, so this is angular acceleration. Angular acceleration. Now, remember, when we brought up a's before, when we were going in a circle, we had two types of a's. We had a that was inward, which was v squared over r, and then we had an a if you were just going around faster and faster. That's what this a is. This one, so if we have an object and it's going around in a circle and it's going faster and faster, this a is the v squared over r. That's from a few chapters ago. But if you're speeding up, you also have an a this way, and this is the a equals r alpha. So don't get these two mixed up right here. Okay, so that is these three relationships. Instead of using s or x and v and a, we like to use theta, omega, and alpha right here. So if we were to come back to our constant acceleration equation, say v equals v naught plus at, and suppose we just switch, and every place you see a v, we put it as r omega, so that would be r omega equals r omega naught plus a, which is r alpha t. Now cancel all the r's and you get omega equals omega naught plus alpha t. Looks a lot like that right there. It looked like all I did was what? Just switch letters right here. If we look at the next equation, x equals x sub naught plus v naught t plus 1/2 at squared. Well, my x, instead of as my distance, I replace it with r theta. R theta equals r theta naught plus r omega naught t plus 1/2 r alpha t squared. Get rid of all the r's, and we get theta equals theta naught plus omega naught t plus 1/2 alpha t squared. So again, these equations look exactly the same. We don't have to memorize any new equations. We just have to memorize how to switch letters. Every place we saw an x, we could just switch it with a theta. Every place we saw a v, we would just switch it with an omega. And every place you saw an a, we'd switch it with alpha. Right there. And all the equations are, matter of fact, all the equations we have for everything is going to be the same. They're just going to be switching letters right here. And then the third equation, we don't even have to go through this. We already know it's v squared, which is omega squared equals omega naught squared plus 2a, which is alpha, times x minus x sub naught, which is theta minus theta naught. So there would be the third equation right there. Okay, so, and you notice when we did constant accelerations in chapter 3, we were throwing it in two dimensions. We were throwing it off in the x and the y. We're not going to rotate about two axes. You're not going to spin this way and tumble the other way. So we're only going to be having it in one plane right here. So I'm not going to have an omega x and omega y. We won't do any of that right here. It's just in one plane right here. So this is what you'd use if you had, I don't know, let's say you have a turntable. Hopefully you remember what a turntable is, something you put a record on, but let's just say it has a motor and it starts spinning faster and faster right here. And you could have said, given that it starts from rest, so omega naught equals 0, and it has an angular acceleration, alpha, let's just say you're given alpha, it tells you how much you're speeding up, and how much, and they also give you the time, and they ask how fast is it spinning after a certain time. Well, I'd probably come up to here. This is what I want to find. If I was given that as 0, it would just be alpha times t. If I wanted to know how many radians it turned, well, I'd probably come in and if once I've got the final omega, I could come over here, plug it into here. That's 0. I know alpha, and then find out theta naught. I'll set equal to 0, and I can solve for the angle. So I didn't give you too many with constant acceleration because it's more important that you get down the energy part. And so I wanted to say, what is the equation for energy, rotational energy? Well, if we come back to our disk, let me just do it over here. And this thing is spinning right here. So this thing, so if you looked at a little particle there, it's going that way. This one's going that way out on the rim, it's going even faster. So if I look at all these, let's just call this 1, particle 2, particle 3, particle 4. This is m sub m, and this is v4. This is v2, this is v3 for this guy, v1. And so if I wanted to find the kinetic of all these pieces, I'm only drawing a couple of them, the total kinetic, wouldn't you just add up all these pieces? It's 1/2 mv1 squared plus 1/2 m. Matter of fact, this one could even be m1. This could be m2 or whatever. So this would be m1 v1 squared plus m2 v2 squared plus 1/2 m3 v3 squared plus. And you remember, energy is a scalar, so this one over here doesn't cancel with the one going the other way, because you don't subtract when you're going the other way. You would with momentum, but not with energy. You just add them all up. So I could simplify this, and I could write it as the sum of 1/2 m sub I v sub I squared. So there's the energy you have when you're rotating right there. Now, I don't want to leave it in terms of v sub i's because the v's are different everywhere. At least if I come over here and write it like this, they all have the same omega. So I'm going to say the ith velocity is the ith r, but I don't have to put an I on the omega because they all have the same. So if we come back over to here, this is 1/2, sorry, the sum. Well, I'm going to put the sum on I can pull the 1/2 out. We get m sub I. V is r omega, so it'd be r sub I squared omega squared. Now I could take this term out because it's not in it's a constant in this, but you notice this looks like our normal equation for the kinetic energy. Remember the kinetic energy is defined as 1/2 mv squared. Well, this is 1/2 times something times a rotational speed squared. Well, why don't we just, what is this thing right here? This must be like, if I compare it to this, it must be like a rotational mass right here. And we could say kinetic energy due to rotation is 1/2 I omega squared. You remember, all the equations are the same, we just switch letters. So we're going to switch our m, which we had before, up there with just an I, where the definition of I is the sum of m sub I r sub I squared. So it depends on the shape of the object right here. So we're going to have I is going to, again, is defined as the sum of m sub I r sub I squared. Now in the book they're going to give you a table for some different objects right here. One of them they're going to give you is for the disk right here. If I were to add these all up, they might do that somewhere in math, but we're not. We're just going to take the value they give you right here. I for a solid disk, is defined as 1/2 the total mass times the outer radius squared. So there's the I for a disk. This will also be our pulley. So when we have pulleys in there and we're rotating it, then this pulley is going to have energy, and what we're going to put in for I is probably the radius of the pulley and the mass of the pulley right there. Okay, we also have over here another shape right here. I've got we've got a hoop right here. The hoop right here, that's a thin hoop right there. I for a thin hoop is just mr squared. Every particle when I spin this has to go fast. That's why this one is larger than that one for the same m and the same r right here. You know, when you have the disk, some of it doesn't have to move very much. The pieces in the middle. And then if we look at a solid sphere, here's a solid sphere. I of a sphere, solid sphere, it's 2/5 mr squared. So you notice all round objects are some number times an mr squared right here. Sometimes I just say I for any round object is squiggly mr squared. What's squiggly? Well, for a disk it's a half, for a hoop it's 1, for a solid sphere it's 2/5, so I can do all of them at one time right here. And a lot of times when you work out problems, the m's and the r's tend to cancel out, and the only thing that really matters is squiggly. They should put that on a t-shirt. The only thing that matters is squiggly right there. So now they also are going to give you some sticks in there. If you have a stick right here, when you spin a stick, it depends on what you're spinning it about. If it's a nice uniform stick, if you spin it about the center, spin it right here, I about the center of mass, it doesn't depend on a radius, it depends on the length of the stick. There's the length of the stick. It's 1/12 m times the length of it squared, right here. But if you were swinging it about an end like this, right here, it means you're swinging around that point, I about the end of the stick, it's even more. It's 1/3, it's 4 times more, ml squared. So they give you a table of all these values in the book right here. So, you know, if you're using a sphere, use that number for I. If you have a hoop or a disc and stuff. Now, here I have this pipe right here. I also have another pipe right here. These pipes both weigh the same amount right here. They're both the same mass. They have the same amount of resistance to shaking. But in terms of resistance to spinning, this one spins really easily. This one spins, this is hard to spin, whereas this one spins real easy. And you notice right here, the regular resistance to shaking has nothing to do with the radius right here. On this one, I got half the mass way out there and half the mass way down here at this end, so I have to get all the mass going fast. On this one, all the mass is right here, and so there's no mass out there. So you can see that they have completely the same round of regular mass, but they have completely opposite rotational mass right there. Now, here I just got this book from the geology department. It's on petrology. It's kind of a dirty book right here. But you notice if I said, what is the eye of a book right here? Well, remember, you have to spin it about an axis. When we were spinning this, it was about this axis right here. When we were spinning the hoop, it was about this axis right here. Eyes are always about an axis. Well, there's an infinite number of different axes here, right here. I could spin the book this way, I could spin it this way, I could spin it that way, I could spin it off diagonal. There's like an infinite number of ways I could spin this book right here. But there's not an infinite number of different eyes right here. Just like there's an infinite number of different colors, but you don't have to buy an infinite number of colors for your printer. You only have to buy 3 colors because you can make all possible colors out of the 3. We call them the primary colors. Well, there's 3 principal ways you could spin this. And because of the symmetry of this, one of them would be like this, spinning it like that. One of them is probably like this, and one of them is probably like this right here. Now, the one that would be the hardest to spin, you notice if you have a lot of mass on your axle, like this sphere, has a lot of mass right on the axle. So this one is pretty easy to, this is the easiest one to spin right here. The hoop right here had no mass on its axle, and it was the hardest to spin right there. Well, you notice if I drill the hole this way, there's not much mass. You know, if I looked at the shavings that came out, there wouldn't be much shavings out of it. So this was probably the hardest way to spin. If I spun it this way, if I drilled a hole through there, I'd get a lot of little dust coming out, so there's a lot of mass on the axle. This is probably the easiest, which means that's the one in the middle. So you notice if I throw it up like this, it's pretty easy to throw it up and catch it right here. Even the one that is the smallest is pretty easy. But what about the one in the middle? The one in the middle, let me just turn it towards you right here. You notice it's very difficult to catch right here. There's no way I can get this thing to spin like this and come back down. It's impossible right here. And which means the middle one, the eye in the middle, is always the unstable one. You might have noticed that with a tennis racket. You throw the racket up and you can look real good and catch it, but if you turn it sideways and throw it up, you got to run right here. So this one here in the middle is always the unstable. You might say, what about the sphere? You could spin it this way, you could spin it this way, you could spin it that way. Which is the one that's unstable? Well, there isn't one in the middle. They're all the same. So there isn't, it'd be kind of strange if you spun it one way and it did something strange right here. If we look at this, there's three ways I can spin it. I could spin it like this, I could spin it like that, or I could spin it like this. But two of them are the same. This one and that one are the same. So there's not one in the middle. I need three different moments of inertia, and the one in the middle is always going to be the unstable one right here. Okay, so that's just with some eyes right there. So.